D7 centripetal and centrifugal forces. Now, let's consider centripetal first. Centripetal force. Now this force I'm going to describe with a simple example of a string attached to a mass, and the string is going in a circle. We have here omega for the angular velocity, and we'll call the mass m, and the string is very, very light. Now, angular velocity, the units for angular velocity would be radians per second. How many radians you go around per second? Like 2 pi per second would be one, say, revolution per second. R is the radius of the circular motion. And we can consider a vector R, unit vector, pointing away from the center. And now I'm going to try to go a little bit here with the velocity into the page. There's the velocity V into the page. And, you know, we also can consider frequency, how many times you go around per second. But let me simplify a little bit, not introduce too many parameters. I do need acceleration though. So this is going to be the centripetal acceleration. Now remember, we talked about acceleration by moving in a circular path with constant speed. And that is the velocity squared over r. And we derived that in an earlier class. So here the force is holding the mass in. So here's the force. And the acceleration is inward. If you recall, the acceleration is toward the center. So if we write down here, let's say we can write down the vector for acceleration is minus v squared over r. When I put the r hat, the little unit vector going outward away from the center, this is the acceleration. And the force that goes with that would simply be the mass times the acceleration vector. And we can write out as minus mv squared over r, and then r hat. So this is the basic setup. The centripetal force is this F, and the centripetal acceleration is the acceleration that goes with that F, which is the v squared over r inward toward the center. Now here, there's no gravity, so this is just like in, say, outer space we were doing this. There's no other forces other than that one centripetal force, the string holding the mass so that the mass doesn't leave the string and take off. So in scalar form, that is when you don't worry about the direction. F is ma. And here, I would like to include the minus sign though with that force to remind me that it does point toward the center. But technically the magnitude of the force could be written as just mv squared over r, but you can include the minus sign like we do in force diagrams, where you have a force to the left, you'll put a minus sign. If it's to the right, you'll put a plus sign. So now let's look at this equation introducing the angular velocity. Now the angular velocity is given by dividing by, let's see, it's taking the regular velocity and dividing by r. This is the angular velocity, and that gets you radians per second. You can think of the velocity as meters per second, and then when you divide by the radius, you're going to get your radians. Now, how is that the case? Well, remember, we've used this formula many, many times, that if you have an angle theta and you have an arc length s and a radius r, that the s is equal to r times theta. Now, if we take the derivative of the left side, we'll actually get the tangential velocity. And then if we take the derivative on this side, well, that's a constant, r would just stay there, and the derivative of the angle with respect to time, see there's your radians, that's going to be r omega. So this is a way to see this formula, that v is omega r. V is omega r, or r omega. So often we see this included, and if you do that, by plugging that in, you get, for the force, you get minus m, and now that v squared would mean you would have r squared omega squared divided by r, and now one of the r's will cancel out, so this is minus m omega squared r. And this is a useful formula to have. Now, what is the centrifugal force? The centrifugal force is defined in a reference frame that's undergoing the rotation. Say, if I am the mass, if I am that ball, and I'm going around that circle, I feel a tendency to want to be thrown outward. For example, say you're in a car, and the car is going to make a left-hand turn. Then you're going to be thrown out toward the door, and the door isn't going to hold you in. But that feeling that you're being thrown out to the door in the opposite direction is a centrifugal force. But that's not a real force, because if you look at this from outside, the car is going in a circle and the door is holding you in, preventing you from going straight. If you didn't have that string there, you would just fly straight. You would just keep going straight at a tangential direction. So we refer to this as a force that arises when you put yourself into the car that's doing the turning. And we call that a fictitious force, because we are in a non-inertial frame. When you have acceleration, we call that a non-inertial frame. And physicists prefer to work and problems out in an inertial frame, in which you see the force here pulling toward the center, and you see the mass, and you have these nice formulas. And there is no fictitious force. By looking at it from outside the frame, there's the car that's holding you in, going in that circular motion. There's no throw out force, all right? Now, if you're in the car, you kind of feel like you're being thrown out, and then the door is going to hold you in. So here we have a little difference in professional analysis of this kind of a problem, because if you're in meteorology, you're on the earth and you're doing the weather and clouds and things. They're going to be in that frame. You're going to find it useful to talk about a centrifugal force. If you look at geodesy, the same thing. When we put ourselves on the planet Earth and we're rotating. So here you have to be careful when that's done. From the physics point of view, the centrifugal force is fictitious, and you really don't need it if you're analyzing the problem from outside, looking at the acceleration. Before I leave this section, I would like to give a force diagram from the reference frame of being inside the non-inertial frame. So here, if I am the ball, I experience a force to the left, and this could be in the car where the door here is pushing me to the left, and I can feel that pushing me in. So this would be the force that is the centripetal force that we have looked at above here. And this force is a real force. However, since I can never move with respect to myself, and I am in the frame moving with myself, so that I'm me, then there's a force that must go in the opposite direction that counteracts this force to the left, so that I am at rest with respect to myself, which must be the case when I'm in the frame of reference where I am. So this is the fictitious force, which is equal and opposite to the real force. And this helps give an understanding of how that force can be very, very important and included in analysis when you're in that non-inertial frame. Like in the case of atmospheric science, or in the case of geodesy, when you put yourself in the frame, then you can consider this force as a force to really be important to contend with. But from the physics point of view, we like to consider this a fictitious force and prefer to be outside the frame of reference. And if you're outside this frame of reference, you're in an inertial frame. You're in an inertial frame, then there's just the one force, F, that's working on that mass, and there's acceleration since there is circular motion. So there's one force, and the force equals ma, and that is mv squared over r. And this is the way the physicists would prefer to look at it. This is looking at it from outside, which is an inertial frame. Inertial just means the frame of reference is not undergoing acceleration. So that's inertial frame. And this analysis here, which introduces the centrifugal force, this fictitious force, this is a non-inertial frame of reference.